regulation today is something totally different and has nothing to do with grid connection rules or grid code issues. Moreover, we return to the German Energiewende and challenges associated with the Energiewende. And I'm with Amprion, as Jasmine said, but Amprion is one of the 4 German TSOs, and the presentation I'm giving now is about investigations which have been performed jointly by all German TSOs. So indeed, I'm now more or less talking for all German TSOs when I report on the findings of our analysis. The agenda of my presentation is as follows. First of all, I would like to introduce to you the objectives of the regulation on reserve generation capacity, which has been established last year by the German government in the context of the Energiewende. And main part of this regulation is the system analysis which has to be performed to identify the needs for reserve generation capacity. And I will report on the results of the 2014 analysis and will conclude my presentations with some conclusions and an outlook. Why do we do this system analysis to identify demand for reserve generation capacity? Well, thanks to the opening session, you are all acquainted now with the challenges of the German Energiewende, so I do not have to explain them more in much detail now, but the basics should be, to recapture the basics, we have a transmission system today in Germany which already experiences, as a consequence of the ongoing Energiewende, strong north to south power flows, because generation units are shut down in southern Germany, in particular those nuclear units by law. But we have heard in one of the presentations in the opening session as well that many fossil fuel generators have problems now with economic situations, and there are many deliberations and intentions to shut them down as well. All over Germany, such intentions become remarkable. And at the same time, we have a rapid increase in renewable generation, and particularly challenging for system operation and system security is an increase of wind generation in the northern part of Germany, onshore and offshore. We have also learned from the opening presentations that in a 10-year horizon, the German grid development plan has identified the necessary reinforcements to the German transmission grid in order to cope with the load flow situations and the market challenges. But how do we bridge the time between today and the future in 10 years? We have a constrained system. We have a very fast changing generation portfolio, and we have grid reinforcement which progresses slowly only, because the realization of grid reinforcement project, building new line, they are very time consuming because we have lengthy permission procedures, and we also face more and more opposition in the public, and we have problems with public acceptance of new lines. All of this results in more or less delay of some important projects, which means that in the meantime we have to do many operational features in order to preserve system security. And if the system, the grid, is not adequate, what can you do in order to cope with constraints and congestions? You have to do market-based measures, in particular generation redispatch, in order to resolve the constraints and to bring the system to a secure state. In the light of this, the German government has established the so-called reserve generation capacity regulation, which shall entitle the TSOs to have the necessary instruments available in order to do the redispatch, market-based redispatch, to be able to maintain system security. Therefore, we need to have sufficient generation capacity available that can be redispatched. And we have learned also in one of the earlier presentations that this could become a problem because of the shutdown of many units, and therefore the reserve generation regulation, capacity regulation, also includes an element that enables the TSOs to prohibit the withdrawal of generation capacity. So they may get out of the market, but they are not allowed to be shut down, but they have to be in a standby mode available to be operated if instructed by the TSOs. And if this is not sufficient, we can also procure reserve generation capacity domestically and abroad as needed for system security. Now it is very important to identify how much of this reserve generation capacity is needed. And as established by the regulation, the German TSO have to do a joint analysis on an annual basis, so this analysis is performed each year, and provides a 5-year outlook on the necessary reserve capacities to maintain system security. We analyze critical grid situations, and from these situations we conclude the amount of generation capacity which is needed as reserve capacity in order to be able to maintain system security. This comes along in close coordination with our national regulatory authority, because what we identify in the second stage has to be approved by our regulator in order then to enable the TSO then in the next steps to start the procurement of the reserve capacities. Well, as I said, as a regulation establishes that the 5-year outlook has to be done, but on the other hand, the time available for this annual analysis is very limited. Actually, as the law says, we have to do it within a 3-month period every year, and therefore we have to pre-select the critical situations which we want to investigate further, because we cannot investigate a whole 5-year horizon there. This pre-selection is often mainly done based on experience from the past. For example, that we know that critical situations can be expected predominantly during winter period. And therefore, we identify on critical points in time within the 5-year horizon where we can reasonably expect such critical situations. Therefore, we investigate, in any case, the next winter, because this is the most urgent question at stake to see will we be able to keep the lights on in the next winter, what will we have to do then. And we select a specific point in times for the further future in the 5-year horizon, where we expect significant changes to the energy supply system, which will have a remarkable impact on system security. And such incidents are the shutdown of further nuclear power plants in southern Germany, which will have particular relevance in this context. And you can see here in the diagram, next shutdowns will be in 2015, 2017, 2019. This is determined by law, and this is the latest point in time when these 3 generators which have a total then of 4,000 to 5,000 megawatts will be closed. And therefore, we have analyzed in this year's analysis within the 5-year horizon not only next winter, but also the winter 2015-16 and also the winter 17-18. 1920 is out of the focus of this year's analysis, but will become then of relevance for the next year's cycle. To briefly explain the methodology of the system analysis, it starts with the determination of the relevant input parameters we need for our market models and network models on which the analysis is based. We define these scenarios, so generation portfolio, load, demand, transmission system, topology in the different time horizons, and agree on them with our NRA The input parameters have to be approved beforehand, before we start the actual analysis, which is then about identifying and analyzing those critical use cases. And as a result of this analysis of the critical use cases, we determine the amount of generation capacity which is needed to maintain system security. And this demand can be further divided into three categories. We have the domestic reserve generation capacity. We identify the secured redispatch capacity we need to procure abroad, because later results will show that the domestic capacity is insufficient. And as a last resort, it is also possible to identify the need to construct new generation capacity in Germany, in particular in southern Germany, as this is an option which is given by the regulation. The analysis of the critical network situations, the steps are shown here on these slides. First of all, once we have identified such a use case, we do the load flow calculations, N-1 in particular, and identify congestions. First, you would normally, what you do when you have a constrained system, you would think about network-based measures. What can you do to release these congestions? However, for this analysis, this toolbox of network-based measures is very much limited, because the challenge or the objective and the task is that we have a network as it is and have to investigate how it can be operated and not how it can be reinforced. The identification of reinforcement measures is a task of the German grid development plan. Therefore, there's only a very few measures are possible here, most related to operational issues, changing topology, changing tap changes of transformers, and then or small measures which can actually be realized in this very limited period of time of maximum 5 years ahead. So the more important areas in order to remedy critical situations are the market-based measures, which are here now divided into the domestic redispatch and the cross-border redispatch. With a domestic redispatch, we first of all redispatch market-based generation, which usually consists of reducing generation in northern Germany and increasing generation in southern Germany to mitigate these strong north to south load flows. And the result of this step then would be the reserve capacity needed in Germany. If this is insufficient, we go further and do cross-border redispatch with our neighboring countries and determine the potential of secured redispatch capacity we need abroad. The critical network situations we have identified can be categorized as follows. Typically, during winter periods, two scenarios, two use cases have proven to be of highest critical to our network. The first scenario can be described as a peak load scenario with strong wind conditions, and the second one is a peak load scenario with no wind conditions. And further analysis has shown that the left one, the one on the left-hand side, the peak load with strong wind scenario, is indeed the most critical situation to our German transmission system. Because during such situations, we have high infeed of renewable energy sources, wind at all, because usually in winter this happens in the evening, so we have no PV generation, we have peak load, and we have many thermal generators still committed in Germany, though they are not needed to cover our domestic load. What the reason behind is that the thermal conventional generation fleet offers into a continental European electricity market, and we have many units which serve as baseload units, like the lignite coal, which makes up more than 20% or 50% of our total generation, and also we have the hard coal units which are operated in a significant volume as well. So in such situations, we see from the transmission grid that we have high exports from Germany to our neighboring countries because of the low generation costs compared to other countries in the European internal electricity market. And this proves to be the most challenging situation to our transmission system. On the other side, in the scenario with peak load and no wind, we have the thermal generator fleet exhaustively committed in Germany to meet domestic load. The conditions of our analysis even show that this available capacity is even not sufficient to cover the peak load in Germany, so we have moderate imports from neighboring countries, but this situation is not as much challenging as the other one to the system. So, what are the consequences and countermeasures to be taken? As already explained, in the case peak load with strong wind, we have the strong north to south load flows in Germany to supply southern Germany, where we have the generation deficiency, and we have high exports to southern neighboring countries, which puts much stress to our system. And in the case of the no wind scenario, the second bullet point is not there, but still we have challenging situations because of the north to south load flows internally in Germany. To make this more visible, I have here on this chart the market balance of Germany at the peak load strong wind condition we expect in winter 2017-18. And we see on the left-hand side the commercial balance of Germany, and on the right-hand side the physical balance of Germany. We have in total export of 13.7 gigawatts to our neighboring countries in these situations. And you also can see that there are strong differences between the commercial flows and the physical flows. Commercial flows can be much higher than physical flows, if you can see there from, with regard to our border to Austria. And it can also be the opposite, that commercial flows are less than the physical flows with regard to our neighboring countries of Poland and Czech Republic. And the difference is the so-called loop flows in the European transmission system, which put further challenges on operation. If you look at the load profile in the German transmission system in this scenario, in the N-1 case, we see that we have widespread congestions in the transmission system all over Germany, which require extensive countermeasures. So all these lines here in either red or the dark colors here, they are overloaded, and measures have to be taken to resolve these constraints. The result, indeed, is that we have to do an enormous efforts in market-based measures to get the system back into a secure state with regards to line loadings and voltage profiles. And some key figures of these market-based measures are listed here. For example, we have to do redispatch of market-based generation in the southern part of Germany of 5.5 gigawatts. We need to curtail wind generation in northern Germany by more than 1 gigawatt. And we need to have a total of secured capacity, the reserve generation capacity of about, or of precisely 7 gigawatts. And these 7 gigawatts are divided in domestic reserve generation capacity, which is located in the southern part of Germany, of nearby 4 gigawatts, and more than 3 gigawatts redispatch capacity to be procured abroad in southern Europe. This table here gives an overview of the results of the analysis for the 3 winter periods we have investigated this year. And you can see that in each period under investigations, the peak load strong wind scenario has proven to be the most challenging one, requiring the highest volumes of reserve generation capacity. and it is steadily increasing from 3.1 gigawatts in winter 2014-15 to 6 gigawatts, and the already mentioned 7 gigawatts then in winter 17-18. On the other hand, we experience that the reserve generation capacity demand in the peak load no wind scenario decreases and actually is 0 in winter 17-18. This shows that the stepwise reinforcement of the German transmission grid has some benefits. We can cope better with the situation in 17-18 than in 15-16. However, this is just a point in time observation I have to emphasize, because we don't know what will happen the next winters, and have to keep in mind that further nuclear power stations in southern Germany will be shut down, which may again lead to an increase in capacity, in reserve capacity, even in the with a no wind scenario, if the transmission system expansion and reinforcement does not happen in time. So the question is, how will the demand for reserve generation capacity develop further? Well, there are several relevant parameters which will determine in which direction it goes. And it has to be assessed parameter by parameter. They have contrary effects there. Certainly, the shutdown of further nuclear power stations will increase the demand for reserve generation capacity. The development of conventional generation capacity in general, we can go in both directions. It depends on where and when new generation, conventional generation in Germany will be built, or when and where existing generation will be shut down. Nobody knows exactly about it, and it is definitely subject also to the future electricity market design in Germany, which is currently under review by our Ministry of Economics. The renewable sources increase certainly will result in an increase for reserve generation capacity, because this will emphasize the north-south load flows mainly, and reinforcement of network infrastructures definitely will reduce the need, because this is a purpose of our reinforcement, to achieve an adequate transmission system. Well, if we actually will observe further increase in demand for reserve generation capacity, what will we have to do? What are the different measures we can take? Well, first of all, we can continue to do what we already do. So we will redispatch market-based generation. We will dispatch reserve generation capacity, which is already under contract domestically and abroad, because this is a reserve generation capacity which has been identified this year or last year in our analysis, and the corresponding contracts have been made. We can procure further reserve generation capacity abroad, but somewhere this comes to an end, because either no capacity is available even abroad, or the volume becomes so high that it is economically unreasonable to go further this way. Therefore, alternative options are that preventive interventions in the market by the TSOs can happen to shift the demand or supply curve, so we can give incentives for generation or for non-generation to the market to result in a more convenient transmission network situation. And one also could limit the German exports, because they have proven to be the main problem here in the high wind scenarios, by introduction or adaptation of market capacities to neighboring countries. In particular, focus on, for such a measure is currently the border between Germany and Austria, because there is no limitation to the market between Germany and Austria. It's a common market bidding zone currently, but this needs to be questioned if the situation evolves in this direction. And as a last resort, one can also think about construction of new reserve generation capacity, typically gas-fired power plants in southern Germany, to cope with the situations. Last slide here, I come to my conclusion. The so far system analysis under the reserve generation capacity regulation have shown that the use case of peak load and strong wind defines the maximum demand for secured redispatch capacity, because in these situations we have experienced in Germany an extreme imbalance between generation and load, which happens because much of the conventional power generation is still dispatched, market-driven due to the low production costs compared to other European countries. The results are the very high exports with a further increasing tendency and the reuse of reserve generation capacity in southern Germany and secured redispatch capacity abroad in southern Europe is strictly necessary in these situations to maintain and preserve system security. Additional interventions to the market need to be considered if the demand increases further, as shown in the previous slide. The north-south flows to supply southern Germany and due to the exports to the southern neighboring countries, we have to state that they increase much faster currently than the reinforcement of the transmission system capacity. Therefore, we experience in total, we are worried about that the situations may get worse until we have reached our target of an adequate transmission system capacity, which will last at least 10 years if projects happen in time, and realistically such situations with an adequate transmission system where you do not need market-based measures in a significant way may happen never, because grid reinforcement always is too slow. Well, those are the results of my presentation. I'm happy to receive some questions now from you.